Hello everyone. Today we will be talking about the new and exciting application of nanotechnology in nanosensors. So what is a nanosensor? A nanosensor can be defined as a sensor that is itself on the nanoscale of 10 to 100 nanometers. It can be a sensor that will detect the presence of nanomaterials or molecules in that size range or smaller. So another question you may have is why nanosensors? Nanosensors are much smaller than conventional sensors, so they could be placed on a small test strip of paper or other material. Nanomaterials improve the sensitivity and speed of detection and detect multiple targets due to their unique properties. As you can see on the right hand side is an image of a human hair, and on top of that is a nanowire curled into a loop. So that gives you an idea of how small the nanosensors can be. Another advantage of nanosensors is the sensitivity or detection range that can range down to just a few molecules of a specific inorganic, organic, or biological material. There are two types of nanosensors, active and passive. An active nanosensor would have the ability to send a signal that could be received remotely. For example, an embedded nanosensor in a stationary position in a water reservoir, lake, or stream could detect the presence of a dangerous pathogen and send a signal. A passive nanosensor, on the other hand, rely on observation of a change in color, opacity, or fluorescence.
There are three types of communication between the nano and macro world. There's nano-nano communication, which represents the necessary coordination and information distribution between advanced micro and nano devices. So for example, surgery microbots would be an example of nano-nano communication, where these bots would have to communicate between themselves. So most of the communication at this level is highly automated. The next type of communication is between macro and nano. So this is when a macro device communicates with a nano device. For example, gold nanoparticles are able to be controlled using macro devices to target and locate tumors, and once these gold nanoparticles are within the tumor, a laser can shine on the gold nanoparticle and heat up a localized area to focus on the tumor and kill the tumor. The third type of communication is between nano and the macro scale. So a good example of this is if a nanosensor collects data from a fluid for pathogens and sends the data to a macro device such as a computer. And this is what the current focus of nanosensors is at, where a nanoscale device is able to process and scan a substance really quickly and be able to send data to a computer where it can be analyzed.
Here are some applications where a lot of research is being done right now. One of which is early disease detection. Nanosensors can be used to quickly and easily get your vital health information. Another important one is early and accurate environmental pollutant detection. Contaminants can be detected in low concentrations and in real time. And then we have defense against biological and chemical weapons, initiated by the Department of Defense, and food quality detection and control, where sensors can be placed in food packaging to make sure they are safe for consumption. Now we will look at some specific applications of nanosensors. Here we have nanobiosensors. These sensors are based on silicon nanowires and carbon nanotubes, and ideally would be capable of detecting molecules at ultra-low concentrations. The potential applications include early detection of cancer and fast sequencing of genome. The sensor surface is functionalized with specific receptors for the target biomolecules. Once a molecule is captured by a receptor on the sensor surface, the current changes in the molecule's presence is known.
Here is an application of nanosensors targeted towards the medical industry. Diabetes is a national healthcare crisis and it is essential for patients to self-monitor their glucose level. Currently, users use a fingerstick method 3 times or more per day. The need to draw blood, or even in small quantities multiple times a day, is not desirable. To solve this problem, nanosensors can be injected using a minimal invasive technology where intra and extracellular nanosensors reside under the skin. Then, a portable imaging device is used to communicate with the nanosensors, therefore eliminating the fingerstick method.
Now here is an example of the placement of environmental nanosensors. Here, the nanosensors are placed underground to monitor the contaminant plume of groundwater. And lastly, we have an application for food quality control. Here, an ink nanosensor is placed inside of a packaged food. When the seal is broken and air is let inside, the ink changes color. This would indicate that the food is possibly exposed to pathogens that would make the food unsafe to eat. Thank you all for watching. I hope you learned a little bit about the future of nanosensors.